Hello, I think we can get started. Hello, good morning and good evening. Welcome to the Data Analytics Colloquium. And my name is Carl Ho. I'm the co-host of the Colloquium. And the other co-host is Professor Peter Pan. Peter, will you introduce the Colloquium and also the event?
Okay, thank you, Carl, Dr. Ho. I'm Peter Pan, Ching Han Pan. I'm from the NCHU, National Chongqing University in Taiwan. And I would like to thank you and welcome you to join us today's stack. Let me just briefly introduce this colloquium to you all. So I think online, maybe they're old friends and new from their friends from the United States side and the Taiwan side as well. The DAC, we shorten as DAC, is supported by National Chongqing University and College of Law and Politics. So we try to invite international scholars and data scientists in to join these online seminars or workshops. So members of the colloquium will engage in conversation with all speakers. So everyone, all the participants today, you're all welcome to throw out your questions after the talk. And today we're very pleased to invite Dr. Tse-min Lee come to us. And then he's gonna share with us a very interesting topic for I think all of us has known about, we've been learning about the p-value for years and years, but now we have need to have a different thought about this conventional methods. So I think this is a very interesting topic. So Professor Ho will introduce, formally introduce Dr. Lin to you all. And before he started, I want to thank you again for participating in today's stack. And if we have any chance or time, and we can try to exchange later after the talk. Thank you. Carl?
All right, thank you, Peter. It is really a privilege to have Dr. Lin to be a very special speaker tonight and this morning. Dr. Lin is the Associate Professor of Government and Associate Director of the Center of Taiwan Studies at the University of Texas at Austin. And he is a graduate of a university in Minnesota. And he has taught and visited many universities, including State University of New York at Stony Brook, Duke University, Michigan State University, and Academia Sinica, the Institute of Political Science, and National Taiwan University too. So his teaching and research interests cover methodology, formal theory, and American and comparative political behavior. He has published extensively in many journals, including the American Journal of Political Science, American Political Science Review, APSR, Democratization, and International Political Science Review, Issue and Studies, Journal of Democracy, and Journal of Information Technology and Politics, and JOP, and Political Analysis. And I do not want to read the whole list. Basically, he published in basically all the top journals and in US and Taiwan. And his research is covering many areas, primarily on political research methods and game theory or formal theory. Tonight, he is going to give us a talk titled The P-Value Controversy. So Peter has already introduced that, but he is giving us multiple perspectives in seeing this p-value we've used a lot. I think without further ado, allow me to introduce Professor Tse-min Lee. Thank you. Dr. Lee. Third.
Thank you. Minor correction. My last name is Lin.
Sorry, yes, it's Lin, and I'm sorry. That is, allow me to correct that. Tse-min Lee is actually his name is Shuangmu Lin, as Lin, yes, to be more appropriate pronounced to be Lin. All right.
Thank you so much, Carl and Peter, for your kind invitation. And good evening from Austin, but good morning to those of you who are in Taipei. It's 8 o'clock in my time zone, and I must say that at this time, my voice is weakening. I had 2 classes during the day. I also had office hours, so forgive me, if my voice is kind of coarse. Okay. I will start sharing my PowerPoint. Okay, so the title of my lecture today, the p-value controversy. I must say that the controversy is not new. Okay, so in this slide, I use the title, the re-emergence of the controversy. It's a re-emergence. Why? As you can see that in 1970, Morrison and Henkel, they already had an edited book with title, The Significance Test Controversy. So that, was 50 years ago. It's a long time ago. Okay. So it's definitely not new. So the question is why? I mean, why the concept re-emerged? Okay. And here I give you a few reasons. There has been a lot of misunderstanding and misinterpretation of p-values. Okay. And I will elaborate on this in a minute. Next, a lot of people practice the so-called stargazing and cherry picking in their quantitative research. Stargazing, you just count the stars. You look at the stars representing the levels of significance, while ignoring effect size and substantive significance. Cherry picking, that means, we do a lot of analysis, but we present and we publish only those findings that are statistically significant. It's called cherry picking. And there is very bad consequences for those kind of practices. And then next, the re-emergence of Bayesian statistics. And in my talk today, I will make it clear why the Bayesian approach is related to the p-value controversy. Finally, there is a replication crisis, which essentially is a scientific crisis because replication is so essential to science that if you cannot replicate scientific findings, we don't know if what we do can still be called science. So those are the reasons, in my view, for the re-emergence of the p-value controversy. Now, here on this slide, I listed some recent criticisms of p-values. These are part of my abstract, which is posted on your website, so I'm not going to repeat. I want to focus here on 4 emerging positions on p-values since the recent controversy. In chronological order, in 2016, the ASA, that's the American Statistical Association, issued a statement on p-values. this is what I'm going to focus on in my lecture today. But 1 year later, in 2017, 72 researchers, they published a paper, Redefine Statistical Significance. They proposed a change from alpha equaling 0.05 to 0.005. Those of you who are graduate students, if you are writing a PhD dissertation, imagine what if your supervisor requires you that all the statistical results must pass the 0.005 level of significance. It's very serious. But 1 year later, 2018, we now have an article co-authored by 88 researchers. In the article, they argue that it doesn't matter whether you use 0.05 or 0.005. Whatever you use, you must justify your alpha. So how do you justify your alpha? And then 1 more year later, we have an article published in Nature, co-signed by 800 plus researchers. They essentially advocate the removal of the p-values, banning p-values from scientific research. Or at least as p-value has been used in a conventional dichotomous way. So you can see that, it's indeed a controversy, okay, because there are at least 4 different positions. So this is why the issue has been so important. It has a lot of consequences on what we do as a quantitative research. So next, for I understand the meaning of us are political scientists. Okay. So political analysis, you know that this is the top methodological journal in political science. Okay. In 2018, political analysis actually banned the use of p-values. Except that later, political analysis stepped back in their instructions for contributors. They say that if your work is based on a kind of design, for example, experimental designs, then it's okay for you to report p-values. Next, from now on, I want to focus on the American Statistical Association's statement on p-values. I summarized their statement into 6 points, and they are so critical. So please allow me to read the 6 points in an ASA statement. Number 1, p-values can indicate how incompatible the data are with a specified statistical model. But p-values do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. Next, scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. So you can think about not just political science research. You can even think about new drugs, how the FDA approve new drugs. Conventionally, p-values are very important criteria. But now ASA is saying that scientific conclusions, business decisions should not be based only on p-values. Next, proper inference requires full reporting and transparency. And then a p-value or statistical significance does not measure the size of an effect or the importance of a result. Finally, by itself, a p-value does not provide a good measure of evidence regarding a model of hypothesis. So the first time you read this, I'm sure you have lots of questions because some of the statements here contradict many people's conventional understanding of p-value. So we need to have some kind of clarification, and that's what I'm going to do in what follows. So let me give you a very brief review of what the p-value is. Originally developed by Fisher almost 100 years ago, the p-value provides a measure of evidence against a null hypothesis, which is usually, but not always, a statement of randomness or no effect. So what you observed is not some kind of true effect, but just produced by random chance alone. That's typically what we call the null hypothesis. But when Fisher developed the p-value significance test, there was only one model. Okay? The p-value was used to test against a single model, the null hypothesis. At the time, there was no alternative hypothesis. So what exactly is the p-value? The p-value is the probability conditional on the truth of the null hypothesis or whatever model that you start with. The probability of observing data as extreme as what was actually observed. So what is important here is that the p-value is a conditional probability. The p-value is not a probability that your null hypothesis or your model is true. No, that's totally wrong. The p-value is conditionalized on the assumption that your null hypothesis is true. In that sense, the p-value is a conditional probability of observing your data given your null hypothesis. So that's the correct understanding of the p-value. So p-value is not the probability of a model. It's not a probability that your null hypothesis is true. Instead, it's the probability that you have observed your data, given that your null hypothesis is true. So as I, told Carl before my talk, if there are questions, may I respond to your questions after my talk? I think that way I have a better control of time. And, it's only a few years later that Neyman and Pearson, they suggested that in addition to the null hypothesis, we also formulate our alternative hypothesis. So that's more the kind of hypothesis that we are doing today. So we have the null hypothesis, the alternative hypothesis. We can talk about type 1 error, alpha, type 2 error, beta, the power of the test, 1 minus beta, and so on. So here is a very familiar diagram I actually copied from Wikipedia about p-value. And you can see that this is the sampling distribution of your statistic. And the center of the sampling distribution is your null hypothesis. Okay? And this point, the black dot, that's your observed data point. And the shaded area to the right of your observed statistic, that's your p-value. Okay, it's one-tailed p-value. And if you're doing two-tailed tests, you have to multiply your p-value by 2. So I'm going to give you an example. Now, I understand that everybody, in basic statistics, everybody has learned about p-values. But let me give you an example anyway. This is a very interesting example. Okay, this is an experiment about the existence of ESP, the extrasensory perception. The experiment was conducted by a couple of psychologists at Duke University. So you take a look at the picture, you see 5 symbols. So the experimenter, they had a deck of cards with equal numbers of cards for each symbol. So the probability of guessing a card right is 0.2. Okay. Except that they ask the subjects to concentrate real hard before they make their guesses. Okay. And they want to see if just by concentrating whether the proportion of correct guesses will be greater than produced what is produced by random chance alone. So that experiment was performed in 1938. It's a long time ago. And overall, the subjects made a total of 60,000 guesses. And the proportion of correct guesses is slightly greater than 0.2, okay? Because 20% of 60,000, that's 12,000, right? According to the law of large numbers, when the sample size is large, the sample mean should be roughly equal to the expected value, right? But in this case, the subjects, they made 12,489 correct guesses. The proportion is only slightly greater than 0.2. it's 0.20815. Except that when you conduct significance test, you formulate your hypothesis, your null hypothesis, no ESP. Cases were correct by chance alone. That means the true population parameter pi equals 0.2. The alternative is that with ESP, just by concentrating real hard, then the proportion of correct cases could be greater than 0.2. And on the basis of the sample size and the proportion observed, turns out that the p-value is 0.0000286. Easily allows you to reject your null hypothesis. If you really believe in p-values, this provides a strong evidence for the existence of ESP. Okay? So how do we make of this? How do we make of this? The problem here, and I hope that I can make it clear to you later. This is misunderstanding and misinterpretation of p-value. Okay. So the way that we do significance test, we typically set a level of significance, call it alpha, and conventionally we use 0.05. And in one-test test, if the p-value is smaller than alpha, then we reject the null hypothesis. And we conclude that the test is statistically significant. Otherwise, if your p-value is greater than alpha, then the test is not statistically significant. So why? What's the reason for you to do that? Well, it seems that this kind of approach is based on the so-called modus tollens in propositional logic. I'm sure we all understand this. Maybe we have not heard the term modus tollens, but we understand the logic. Okay? Because we all know that if P then Q, then if not Q, then not P, right? That's what is called modus tollens. Okay, but in propositional logic, this is actually deterministic modus tollens. There is no probability elements here. Okay? If not Q, therefore not P. But in the p-value or significance test, we actually allow for some probability. So if we agree that we are following the logic of modus tollens, then it's not deterministic modus tollens. It's actually stochastic or probabilistic modus tollens. And because P smaller than alpha, a very small probability is not exactly the same as impossible. Okay? However small P is, there is still a probability. Okay? And that's different from being impossible. So that's the critical difference. And I believe that this is well known table or chart here. I learned this in basic statistics. I teach this to my undergraduate students in basic statistics. Okay, so here you have the null hypothesis. The null hypothesis may be true or may be false, and here you have your test. The test may be positive or negative. Okay. If the test is positive, okay, then the null hypothesis is rejected. Otherwise, it cannot be rejected. So we have type 1 error when the null hypothesis is true, but it is rejected. We have type 2 error when the null hypothesis is false, but it is not rejected. Okay? And alpha, or therefore significance, that's the probability of type 1 error. And beta, that's the typical notation that we use for the probability of type 2 error. And also alpha is also the probability of false positives. Okay? Because the test is positive, but it's wrong. So alpha is the probability of false positive, and beta is the probability of false negative. Now, when you see the words positives, negatives, then I don't know if they remind you of the COVID-19 test. Okay. So if they do, then I don't blame you, because in a minute, I will show you an example relating COVID-19 tests to significance tests. But before I do that, after understanding what p-values are, let's take a look at what p-values are not. And according to ASA, I just read their statements to you. P-values can indicate how incompatible the data are with a specified statistical model, but p-values do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. And in terms of mathematical notations, p-value, as I told you, is the conditional probability of your data, of observing your data, given that the null hypothesis is true. The p-value is not the probability that your null hypothesis is true, given the observed data. And that's very different. The two probabilities are very different. Alpha, that's the probability of false positives. I already told you that. But now I want to introduce a new concept, and that's the so-called inverse probability of false positive. The inverse probability, if you look at the probability of false positives here, if you exchange the two items on both sides of the vertical line, then you get a probability that the null hypothesis is true, given that your test is positive. This is called the inverse probability of false positive. So if you tend to think that p-value is a measure of the probability of the hypotheses that you are studying. I already told you that that's wrong. P-value is not the probability of a model or a hypothesis. P-value is the probability of observing your data given your model. If that is the case, then how do you compute the probability that your hypothesis is true? If you want to develop a measure of the probability of your model or your null hypothesis, how do you do that? Well, here is what you should use: the inverse probability of false positives. Because according to the definition here, this is the probability of your null hypothesis given your data, given that the test is positive. Okay? And in general, the two probabilities are not equal. So here the question is how you calculate the inverse probability. You need to use Bayes' field. That's why Bayesian statistics is so critical. Why the reemergence of Bayesian statistics in recent years has, influenced the reemergence of the p-value consequence. Okay. So as I promised, I showed you an example from the COVID-19 medical test. So here, we have an individual who may or may not be a carrier of COVID-19. So yes means that the individual is a true carrier. No means the individual is not a carrier. Now the individual is subject to the COVID-19 test. Okay. And the result can be either positive or negative. So once again, we have four possible outcomes, right? If the individual is a carrier and the test is positive, okay, it's great. The medical instrument correctly identify the carrier. And if the individual is not a carrier, but the test is negative, okay, and once again, the instrument did its job. But in the other two scenarios, the test results are wrong. So here in this scenario, when the individual is not a carrier, but the test is positive, it's false positive. And in this scenario, the individual is a carrier, but the test is negative. So it's false negative. Now, the quality of the testing instrument, I believe that many people, they are now familiar with the two concepts, specificity and sensitivity. Those are the terms used in medical examinations. And in this particular example, I assume that specificity is 95%, sensitivity is also 95%. Both sensitivity and specificity, they jointly represent the quality of the testing instrument. The higher, the better. compared with statistical test, specificity is really 1 minus alpha, because the probability of false positive is alpha. So you have 1 minus alpha. And sensitivity, that's really 1 minus beta, because this is your beta, that's the probability of false negative. So there was a lot of understanding, during COVID-19 that, if an individual tested positive, that doesn't really mean that the individual is killed, because there is a possibility of false positive. And if an individual tests negative, and then once again, it doesn't mean that the individual does not carry COVID-19, because the testing result can be false negative. So the question is, then how do you make sense of your testing results? You need to calculate the inverse probability of false positive. And that means if you test positive, if an individual tests positive, then you ask, what's the probability that the individual is not really a carrier? And the result can be very unintuitive. Let me show you. You need to use Bayes' theorem, because of the probabilities that I provided here, they are column probabilities. They are conditional probabilities based on the assumption of whether the individual is a carrier or not. But that's not what you want to know. What you want to know is, given that the test is positive, what's the probability that an individual is a carrier or is not a carrier? So you need to reverse the order in calculating the probability. And you must use Bayes' theorem. Now, in order to use Bayes' theorem, you need to have something called the prior probability. The prior probabilities in medical examination, in particular this number, is called preference. How widespread the disease or the virus is. And in this particular example, I use 0.06. That's about, the preference in many American cities. And as far as you have a prior probability here, then you can apply Bayes' theorem and compute the inverse probability. Turns out it's 45%. Okay? So if the sensitivity and the specificity of the testing instrument is 95%, it's very high, and an individual tests positive, then conditional on the testing results, the probability that the individual actually does not carry the disease is as high as 45%. Just very counterintuitive. Okay? Let me move on. So we can apply the same procedure of calculating the inverse probability to significance test. And here I give you the formula. You can see that in order to calculate the inverse probability that the null hypothesis is true, given that the test is positive, you need to know alpha, you need to know the power of the test. You also need to know the prior probability in terms of the prior probability that your alternative hypothesis is true. That means even before you conduct your test, you need to know how likely that your research hypothesis is true. You might have questions about how you get to know about this prior probability. And I will answer that question during Q&A. So given the way that we calculate the inverse probability, I can show you some very interesting result. In this diagram, the vertical axis is the inverse probability of false positive. The horizontal axis is the prior probability that the alternative hypothesis is true. How likely that your alternative hypothesis is true. And I use the formula here to produce three curves, each corresponding to a different level of beta. But in the diagram, alpha is set at 0.05. And from the diagram, you can see that when the prior probability of alternative hypothesis is very small, then the inverse probability can be very high. It can be as high as 0.8, 0.9, even though you are using alpha equal to 0.05. This tells you that when the prior probability of your alternative hypothesis is low, then alpha can severely underestimate the inverse probability of positive. Now, next, I use some numbers to give you a clearer picture. You can see that, with the same parameters, if you want to get an inverse probability of false positives about the same size as alpha, 0.05, 0.063, 0.091, then the prior probability of your alternative hypothesis must be as high as 0.5. Next, I did something similar, but this time I set alpha at 0.005. And you can see that the curves, they drop much faster in terms of numbers. Here, if you want the inverse probability to be about the same level as your alpha, 0.005, you still need the prior probability of HA as large as 0.5. And here you have 0.005, 0.007, 0.010. However, if you're happy with the conventional alpha of 0.05, then the requirement on the prior probability of HA is not so demanding now. As far as the prior probability of your alternative hypothesis is 0.1, then your inverse probabilities, depending on beta, can be roughly the same as the conventional level of significance, 0.05. Okay. So you can see that this is a big reason why some scholars recommend using 0.005 as your level of significance, because it will not be so demanding on the prior probability of your alternative hypothesis. Okay. So I have about 10 minutes, so let me summarize my analysis here. Firstly, when the prior of the research hypothesis, HA, or alternative hypothesis, when the prior is very small, alpha can severely underestimate the inverse probability of false positive. And I can go back to the ESP example that I showed you a while ago, right? The Duke experiment of ESP. The p-value is so small, okay, that you can reach statistical significance at a very low level. However, in an experiment like that, ESP, let me ask you, what's the prior probability that your alternative hypothesis is true before your experiment? To what extent you believe in the existence of ESP? Do you have a strong theory for the existence of ESP? If there is, I don't know. We don't have a theory which tells us that just by concentrating real hard, we can actually produce extrasensory perception. And we can increase the proportion of correct guesses. We don't have a physical theory like that. We don't have a theory which tells us that by concentrating real hard, then some kind of electrical magnetic wave will be produced, which will allow you to make correct guesses. We don't have a strong theory. And that means the prior probability of your research hypothesis, ESP exists, is very small. And the conventional level of significance, alpha, can severely underestimate the inverse probability of false positive. Next, if it is desirable to keep the inverse probability of false positives at the 0.05 to 0.1 level or smaller, then the choice between alpha equaling 0.05 and alpha equaling 0.005 depends on the prior probability of research hypothesis. If you have strong theory, if you have a strong substantive reason to support your alternative hypothesis, then the prior is high. Then alpha equals 0.05 is appropriate. But if the prior is low, like somewhere between 0.1 and 0.5, then maybe you want to use alpha equaling 0.005. However, there is a kind of trade-off between using alpha equaling 0.05 and alpha equaling 0.005. If 0.05 is justifiable, but you use 0.005, then the cost is going to be large, larger beta and larger sample size. Okay, if you have to conduct a survey, instead of 1,000 respondents, you might have to interview 10,000 respondents. And let me ask you, do you have that kind of money, to conduct a survey of 10,000 respondents? We don't. Conversely, when alpha equaling 0.005 is justified, but alpha equaling 0.05 is used, then the cost is that alpha can severely underestimate the inverse probability of false positive. This is true. Okay? So that's the reason why some scholars argue that, we don't want to have one size for all. Whatever you do, just justify, okay? Depending on the prior probability of your alternative hypothesis. But there is another, consequence, which I am not having enough time to elaborate, but I can read it to you. This has to do with cherry picking, or so-called multiple hypothesis test. If you know hypothesis is true, and you use alpha equaling, say, 0.05, but the probability that at least one test is significant is often much greater than R. And here I give you an example. If you perform 20 tests of the same hypothesis, for example, you might want to twist your model a little bit. Okay? Use the same research question. Use the same dependent variable, but you just twist the right-hand side of your equation a little bit. For example, you may drop some independent variables, or you might add some other independent variables, or you might take log on one of your independent variables, or you might introduce an interaction term. And you estimate all the 20 models, and you report the one that gives you what you want, the significant one. Here I tell you, even if you know hypothesis is true, the probability that at least one test is significant is 0.64. Okay? That's called cherry picking. A lot of people do this. You ask yourself, and I will ask myself, whether we have done this before. Nowadays, it's very possible that a computer program can produce 100 models or 1,000 models and gives you the results of your explanatory variable. And maybe in 1,000 varieties of your model, only one in which your explanatory variable is statistically significant. And you report that in your manuscript, and you got accepted. That's quite possible. It's cherry picking. Okay. So what can we do? According to American Statistical Association's suggestion, we'll use confidence interval, credibility interval, prediction intervals. Or you give up on frequentist approach, you give up on p-value test. You just use the Bayesian approach. Okay? You use other alternative measures, such as likelihood ratio or Bayes factors, but that is not really a good solution. You can use other approaches such as decision theoretic modeling, and force discovery rates, I don't want to get into this. I'm just repeating, what the ASA suggested. If you want to understand the rationale for this, please read the ASA article. And here is what a lot of people have been doing. Nowadays, when I participated in a conference, almost all the papers, they report the confidence interval diagram, right? Carl, we were on the same panel a couple of times recently, right? All the panelists, they report confidence interval. Okay, so the conclusion of the ASA statement: good statistical practice as an essential component of good scientific practice emphasizes principles of good study design and conduct. A variety of numerical and graphical summaries of data, understanding of the phenomena under study, interpretation of the results in context, complete reporting, and proper logical and quantitative understanding of what data summaries mean. No single index, not even p-values, should substitute for scientific reason. Okay? So that was the ASA's conclusion. My conclusion: the perils of p-value dependence. If you rely too much on p-value, it can be dangerous. Okay? For your research and for science, it can be dangerous. The importance of theory and context, because now we understand the role of the prior probability of research hypothesis. If your alternative hypothesis is strongly supported by theory and context, then you're going to have higher prior probabilities. And that means 0.05 may not be such a big problem. And you want to conduct the robustness test. Okay? You want to change the model a bit and see how robust your results are. And you want to make your results transparent to everyone, including the referees. The relevance of non-findings. So far, most of the journals, they only publish findings. They don't accept manuscripts based on non-findings. But now we know that non-findings are as important as findings in a scientific enterprise. And we must make our research fully transparent. Okay, that concludes my presentation. Here is just some humor after a long monologue on my part. Okay, and thank you. Now, let's see what kind of questions we have. Carl or Peter?
All right. Okay. Hello, can you hear me now? Okay. I think it's time to open up for questions or comments. But one remark on the last picture. Do you recommend the 21st century scientists to shave? We cannot keep any bear in order to make sure you identify as a good scientist.
We want to go back to the old time, the good old time. things. Okay, nowadays, the computer is so efficient. We can estimate 1,000 models in a few minutes. Okay.
Yeah, indeed. Yeah.
Because we can do that, we don't use the kind of rigorous scientific reason. We are more likely to be doing number crunching. Okay, so maybe having some beer.
Okay, now this is a section I think will allow some questions from both sides, the U.S. and Taiwan. Please feel free to ask questions. Either if you're too shy, you can just type up in the box, in the chat box, or you can speak up, which is what I prefer. Now, Tianyi has some suggestions, and Tianyi would like to
sure.
recommend questions. Yeah, Tianyi.
Sure. Thank you, Dr. Ho. Oh, Dr. Ling, it's a phenomenal presentation. You did blow our mind. I have to say that. Well, I'm from Dallas. I'm Dr. Ho's student, 30 years PhD student. So, I guess you make a good point that computer, computing capacity would make some change to the Dr. Ho called 21st century scholar. Well, I also have the same feeling. I just happened to read a public administration article this afternoon, and they used to use this is a factor analysis study. They used to use by default. That's the word I really hate. By default, they use the orthogonal rotation.
Yeah,
people use that because in the back to the 1950s, 1960s, we don't really have that capacity. It's easier to assume that the factors are the components are has a 90-degree relationship. They're unrelated. That's assumption. But in the reality, we will practically we do see that factors can correlate. So then scholars start to suggest that we should stop assume that we should use orthogonal rotation. We better as the default we should use the Aldine mean for instance rotation. So that's the logic is the same. I think you're making a good point that you're suggesting a tipping point that we should move forward to have a more robust data or method to make a better scientific research in general. So my question for you is, which area, like which specific area of study, for instance, business or social science or medical research would make that movement from your understanding?
You mean changing
the rule from say 0.05 to 0.005? Which area would be the leader?
The articles that I mentioned, in my slides. Okay, as a matter of fact, I can make available my slides, so that everybody can download a copy. And on the slide, I actually provides hyperlinks. So by clicking, you can get the article online. But my point here is that those articles were not published by social science journals.
Mm-hmm.
They were published in life science journals.
Mm-hmm.
Okay, scientific. Okay, so I think there is a reason for that. Especially say the medical test that I provide as an example. And also about drugs, vaccines for preventing, COVID-19. Nowadays, we realize how important those vaccines or drugs can be. They can actually save human race. Okay? But how exactly were certain drugs or certain vaccines approved? I cannot claim to be an expert in that regard, but I can tell you, as far as I know, p-values. And so if we agree that p-values have their problem, but such a statistical tool is determining what kind of drugs, what kind of vaccine can be approved, can be authorized by the government in order to. So you can see how it can rely on a single measure. So I guess that's the reason why people in that area, they are really keen to.
Okay. Yeah.
Thank you, Dr. Lin, Dr. Ho. I appreciate it. Well, I was saying from a behavioral economic perspective, well, I can definitely see a good reason that we should move forward for a better scientific threshold and to get more robust result. But I mean, my worry would be, say, like I'm from public administration field, and I can see that some PA scholars that they kind of afraid of getting out of our comfort zone, if you wish. We're just very used to this, the p-value rule, the traditional p-value rule. And if we say something or make some novel prediction, or like say make some statement based on a 0.05 p-value, we can just tell this. It really depends on your storytelling skill. Like, hey, we get a very good p-value, and then next we how we want to tell the story. Then if the story is good, it's convincing, then we can good to publish a good paper, right? So I mean, I don't see that the scholars in our field would move forward to jump out of the comfort zone. So for how would you sell or nudging? I use the word nudging, and this theory to like the social science.
I understand.
You see my concern?
Yeah, sure. But one step back. The kind of so you said you're in public administration, right?
Correct. Yes.
The approval of drugs and vaccines, these are a part of public administration, right? It involves the FDA, procedure, right? So now we have a better understanding of the importance, the seriousness of the approving procedure. So, the solution, to your question is that the government, of course, they need to enhance the criteria. They need to make more rigorous, more strict. But not only the government, but also academics, journal publications. As academics, we aspire to publish, right? And if the journal editors, if they are willing, like political analysis, like the psychology journals I mentioned, if they are willing to increase the threshold by increasing 0.05 to maybe 0.01, if not exactly 0.005, that actually I know that most of us submit our articles to political analysis, or many of us may not even read political analysis because those articles are just so technical, right? But even AJP has made a point that you cannot use 0.1. A lot of us I'm sorry to say that maybe in Taiwan, I done reviews for journals. I have seen a lot of images showing 1 star or up or achieved at 0.1. EJPS specifically banned 0.1. Next time you submit your article to DP, if you use 0.10 in your manner, it will get banned. That's my view. Okay.
All right.
So,
okay.
Thank you, Dr. Lee.
All right. Can we have any questions from Taiwan side? Peter? Can I hear you yet?
You need to unmute. Peter, you need to unmute.
Sorry about that.
Okay.
Yeah.
We can.
All right. Can you hear me now?
Yeah, I can hear you.
I just said that Tianyi pretty much mentioned the question that we have here, because it's about the subjects like the medical, social sciences, things like that. But something's related. What is conventional p-value statistic is still prevailing, giving the prevalence of the misleading results that you might cost, and and then yeah, it's about the subject or the field, because it's medical researchers, because some, if not all, or most medical researchers adopt a much smaller p-value, like 0.005 or 0.001, so to draw conclusions. So isn't that related to the subjects about the report or the researches? In the social science researches, probably people accept 0.05 as an acceptable probability. Of course, it might be misleading, but it's acceptable. But in terms of the medical researches, people are not accepted 5% of wrong probability or false positive is not acceptable. So it's kind of field sensitive. Is that the reason why this inverse probability of false positive is not kind of everyone is accepting it, or all the journals are accepting it? Instead, the p-value, the conventional one, is more prevailing in our field. So that was the question.
I think so. I mentioned about one article, with lots of authors, and they said just why your alpha. Okay, so justify apparently scholars in different disciplines. They can use different justifications, right? In social science, maybe our research is not really so crucial. But in medical science, in life sciences, the consequence is huge. So I understand the rationale for that article. Justify your art. There is no one side.
Thank you. Yeah. Carl, do you have a question of your own?
Oh, of course. I have some questions, a lot of questions. Now, I think you raised some good points. Now, I need to number one think of the trade-offs, and I think p-value was widely accepted because of the ease of use and also easy to convey the idea when you have multiple hypothesis tested simultaneously, such as like a multiple regression. And there are other trade-offs, like you can use other tools, such as I think recently they're more using sensitivity and specificity, like a ROC curve or the area under the curve, and try to see whether you can achieve both. You can get high sensitivity and specificity is taken care of too. So in that case, that means you carry in a lot of statistics in order to provide a fuller picture. So how do you strike a balance? And I think I understand that we can, why don't we put it to 0.005 instead of 0.05? But in the meanwhile, it makes it difficult make it slightly more difficult to convey in the story. I think that the beauty of doing the 3-star is stargazing, looking right now, and multiple hypotheses being tested. You can see a bigger picture. And now I think there are other conventions being built, like using the coefficient plots, and you suggested that too, and looking at confidence intervals, whether it touches the 0, and that is something. What do you think about a trade-off, and how do you make the next generation of data presentation, and what is the most efficient way of doing that? Yeah.
Well, I am sympathetic to the argument that p-values can be quite misleading.
Yeah.
Especially as a teacher of undergraduate basic statistics, the concept is very difficult to teach to undergraduates, and many just rely on incorrect understanding.
Yeah.
So I'm sympathetic, with the position. Maybe we should rely on alternative approach. I don't want to go as far as banning multiple methods. I think that's good. So in addition to you use a confidence and the p-value, mathematically they actually include the same input. I don't believe that confidence carry more in but the difference is not in the amount of information, but in visualization.
Yeah.
With p-values, you have table, you have stars in there. Then people just look at the stars.
Yeah. It's not gazing. Yeah.
But confidence interval, when you see the confidence interval plot, as you in my slides, not only that the confidence interval, you also see the point estimate.
Yeah.
And so you get some idea about how large the point estimate is. For example, if you have 2 different drugs, the first one is statistically significant, effective, but the effect size is very small. So the point is very close to 0, but the confidence interval is also small. So the 0 is outside. And the second drug has a huge point estimate, but also with a huge confidence, such that 0 is included, even though 0 is very close to the lower limit of the confidence. And if both drugs cure the symptom, let me ask you, which drug would you prefer? The one with the significant but small effect, or the one insignificant but with a potentially large?
Of course, I do not want. Yeah.
But if the FDA in approving drug, if they stick to the conventional threshold, 0.05, the first drug will be, while the second drug will not. It's a big concern. So that's why I think that even though the confidence contains the same information as you know, the pValue table, which showed it. But I think confidence in terms of region.
Important
but
point.
We're not just choosing between the two. We are arguing that, or ASA in its statement is arguing that you need to use multiple methods.
Yeah. All right, and 10 years, yeah.
If you give me one more minute, I can freely admit that in the 1990s, I published an article in Political Analysis. I used an event history model. In the MLE, the maximum likelihood estimate, the explanatory variable and the coefficient associated with the main explanatory variable is not statistically significant. But I got published in Political Analysis. Okay? And, you know, maybe I'm lucky, but I'd like to think that, you know, in addition to that piece of information, I provided a lot of other information that are consistent, you know, with the sign of other coefficient. I still think that that approach should be used.
All right. Okay, good. Tianyi, you have a hand up? Yeah, go ahead.
Thank you, Dr. Ho. Dr. Ling, I have a follow-up question, I guess. Well, the story goes, yesterday we have a structure creator model class with Dr. Ho, and I got picked on by a guest speaker, Dr. Jill from American University.
Yeah, Jeff Gill was there.
Right. I got picked on because I asked a silly question and about the p-value. But anyway, so in the what was the current status in the political science study when say we're going to publish submit an article? What's the output that the reviewer or you know the editor would like to see? Confidence interval or but not p-value, right?
It depends, you know.
Okay.
I just said that in conference, most show confidence. Okay. So confidence interval plot have been very widely used, and that's true. But I still, you know, when I reviewed manuscripts, I still see papers or manuscripts with only tables and stars, okay, but not confidence interval. So, you know, I don't know. You can just pick up your preferred journals and see what they report. But, you know, if you allow me, you know, there is one more that I can make. Response to your first question about what can be done to help doing things right. As far as I know, some journals have been promoting pre-registration I don't know if you have heard.
Yeah. Mm-hmm. Yeah.
Reemerged.
Mm-hmm.
What it means is that even before you get your grant, before you acquire your data or before you write your manuscript, you must register your research design online. Okay? So in registering your design, you would make your model very clearly specified.
Mm-hmm.
And there are lots of websites that provide. Once you register a design, you cannot change. And so, once you register, you apply for your grant, you got your grant, you collected your data, and you run your analysis. You must stick to what you originally.
Mm-hmm.
So
Yeah.
some journals, I don't think a lot of journals require it, but some journals might prefer. I have seen authors, they claim that my research
Mm-hmm.
and they can. So that will increase the confidence of the editor and reviewer in your because if your design has been pre-registered, then there is no way for you to do it, right? But you must stick to your original model specification, and that might be used. If pre-registration has become a requirement, that will be a disaster for many of us. Okay. But if it's just an incentive for getting accepted, by referees and journals, a lot of people might voluntarily do that, and that helps.
Well, thank you, Dr. Lin. That have my answer too, and my question too. Appreciate it.
Yeah, good suggestion. And now more and more journals are accepting pre-registration, and maybe we can talk more about this and provide more resources about pre-registration to register your model before sending for publication. Yeah, it's a good suggestion. Peter, do you have any questions from your students? More? Or from yourself?
Not for now.
If they, I don't know whether it's appropriate, but if speaking in English is difficult for Taiwanese students, maybe they can add in Chinese, and maybe you can translate for them, but I certainly will be able to understand your question.
Yeah, sure. Yeah, I talked to them about this, but some of them are not well equipped with, the statistical, they have the background, but they are learning it. Some of them are kind of, not using the quantitative methods that frequently. So they're just listening, but a couple of them did raise the questions that I just passed to you. Also, I just FYI for those who read Chinese can check out Professor Lin's blog, right? And I think we checked your blog, and then you did mention you have an article mentioned about this this subject, right? And the 菜市场政治学, another copy of the same article. So for those who read Chinese, please, you're welcome to read that article. You can get the gist of what Professor Lin has talked about today.
Thank you.
Hey, Tse-min, you should talk about it. You should talk about it. How many hits in China now?
Yeah, thank you for reminding me that, you allow me to do that. It started with a talk that I gave at National Zhengzhi University. Okay, so that's the first time I talked about p-values. That was a few years ago. And then, they have a journal, so they transcribed, my speech, and they published my speech in the journal. Okay. And so I reblogged that article in my personal blog. And but a couple of years ago, when political analysis banned p-value, then I post on my personal Facebook about the news that political analysis banned p-values, and I also shared the link to my article. In a couple of days, the article was, you can say, plagiarized in China, in or Weibo.
Yeah.
And that's fine. That's fine with me. I'm happy that people are interested in my work. But beyond my imagination, in 2 days, the counter reached 100,000. 100.
Can you make money out of that?
I received invitations from universities in China for me to go to China to give talks on that topic. So you can see, in China, there are lots of people. I mean, China is a big country with a huge population, but still, they pay attention.
Yeah. All right, then. I hope this YouTube may make some good hits too for our colloquium. If we can transcribe it in Chinese, and this is something we can get some popularity to. All right, I think, can I invite more questions, anyone? And then I think we have invited Dr. Lin to UTD for field talks. I think one of the most welcome ones is still the p-value controversy, and also that talk arouses some reflection on how to report and or how to model in the first place, how to think about a model in the first place, and how to report and statistical findings, whether using methods. So since then, I start teaching students to use plotting the coefficient plots, look at the confidence intervals. Nowadays, I think more can be done using ROC. I think no, I'm sorry. There's an AUC. This is the area under curve, and that is reporting both sensitivity and specificity. So this is something I think we should do, and also in my machine learning class. And nowadays we basically use AIC, BIC, and also AUC or the curve, and to report both. And maybe that should be the direction too when you go beyond the asterisk and report the sensitivity and specificity. Yeah. And it should be very easy to implement too nowadays, and R can do that, and Stata can do that. Tianyi, do you have more questions? Follow up? Go ahead.
Thank you, Dr. Ho.
Yeah.
Well, we would not be surprised if Dr. Lin become a YouTuber. But yeah, I found the article that you were talking about. I'm from mainland China, so I have the access to. It's called Zhihu. It's actually got 100,000 clicks. Wow.
Yeah.
But anyway, I do have a follow-up question for you, Professor Lin. I'm from a business major. I have a marketing BA, BS, and I was a marketing manager prior to my journeys as a ET Dallas PhD student. So my question for you is, what would you comment on, say, the businesses? Sometimes they use like 0.8 as their critical value. And
0.08.
No. So it's 0.20. Yeah,
I see.
So to me, they're different. Like when we talk about the misleading information, well, I guess for the social science and for the medical, my reasoning would be for the medical school, they probably need a higher, a more strict threshold, but for social science, we have more tolerance to those misleading or misunderstanding, but for the business, it's not the same logic. Like they want to make money. They want to get the best model to make their business efficient. But why they're using, like, what's your comment to them? Like, they're using like a 0.2 as their p-value, if you wish. Thank you.
I think I make some comments, but I don't claim to be an expert in theory. Now, we also can talk about data science. I gave another talk to several institutions about the evolution of political methodology.
Mm-hmm.
So, inevitably, I will talk about the current popularity of data science. The way I see it, there is a difference between data science and statistics.
Mm-hmm.
Now, at Austin, we have a department of statistics and data science. And actually, you can see that statistics and data science, they are not equal. That's why the department is both. So what's the key? I think one of the key people who do this, they are more interested in making.
Mm-hmm.
And while people who do statistical analysis, they are more interested in doing prediction versus statistics. So I see some, published material in data, and they use statistical model, but they don't necessarily focus on statistical. Why? Because statistical influence is not so important then. To people, because as far as their data is big enough, they can use data, right? If their sample size is big enough, if they can cover a lot of data in that area, and they can succeed in predict what they don't have to worry much about time. And maybe I'm wrong, but I tend to think that in these, maybe that's what is giving them outcome. I mean, you can tell me, I don't know, but the word business strikes me as very interesting, more in, profit, right? Sale. And if a model can successfully predict sales outcomes, profit outcomes, it's good enough. Who cares about data? Is that reasonable? Can
Yeah. Thank you, Dr. Lin, Dr. Ho. I appreciate it. I guess one back to Dr. Ho's question previously. I guess they're making trade-off too. Like the business, they won't find a good point that their investment on the actual sample size, or well, they want good sample size, but the marginal investment on the sample size no longer turn to some profit, or no longer make their model better. So what was the incentive for them to invest money on something not that important, or But I got your main point. Thank you. That's so much helpful. Yeah. I appreciate it, Professor Lin.
Yeah, let me add a footnote. Tse-min, I think somehow your speech may be broken a little bit, and because of the mic or maybe the connection. I think your point is well brought home in data science versus statistical modeling. And data science is the simple goal is to do a prediction and do the machine learning, and then get the right prediction and accurate prediction. While statistical modeling is still more on the inference and explanation of the of individual variables. So, but I don't think they are something not bridgeable, not communicatable. Actually, more recent development is to bridge the two culture, like Leo Brayman suggested, and you can draw inference, then make your prediction more interpretable, more supported inference. And I think that's why more and more departments are combining statistics and data science instead of just doing data science to do prediction only. They need to have the statisticians to back them up and to make them something more interpretable, more inferential. So nowadays, I think we have a we teach something called interpretable machine learning. And if you get a black box, you can predict, but you cannot interpret. That is something still a miss to a lot of data scientists. Maybe this is something we need you to come back to give another talk. How do you bridge that and combine inference and prediction? And that's something really interesting and for our audience too in the future. Yeah, and now I think we have a few more minutes. Let me invite more questions or comments or feedbacks, and then I think I will let Dr. Lin to wrap up to give any conclusion, and yeah. Okay. All right, could be my mic too. Okay.
Yeah. I understand that my mic. Yes, my mic may have a problem. Let me see if I can fix it. Device settings.
It could be my problem. Could be my speaker. And yeah. Peter, how's your side in comparing to the sounds?
It's pretty clear here. Yeah.
Oh, okay.
This.
My
voice, is it better? I changed the mic.
Mm.
Yeah, this is good. This is good to me. Yeah.
Good. Yeah.
Okay.
Now I
Yeah.
get well.
Yeah. Okay. Now, do you have more questions, guys? And Peter, you have any suggestions or remarks? Yeah.
No, just I think this is just a comment. I think from the floor, from the classroom. Says that, yeah. All right, this is social science because we're all social scientists if we claim it, and I think the alpha or p-value is more like the risk that we're willing to accept, right? The risk of making wrong decision, because we talk about the robustness and things like that is very quite technical, but come down to decision making, right? Whether it's the medical one or the business one or the social science one or policy one. So it's about the risk that we are willing to accept, the risk of making wrong decision. So I think in terms of the publication of journal, and it is like they will have to come up with some threshold, right? It says that we accept a lower p-value or a higher p-value. Otherwise, there's no a guideline. They have to set the guidelines for you and I and whoever wants to submit the article. So I think that's the thing. Eventually, maybe it's not a only one standard like alpha equals 0.05. And then each and every journal has to determine which level they would accept. And then for those who want to submit the article, they have to look into the guidelines and say, all right, if I'm the journal I'm going to submit, and then I have to go with the rules, right? And so there's different kind of things, and that's pretty much a comment. It's not a question though. It's for us to think about. Yeah, thank you.
Thank you. Thank you. I think I can, on top of what you have said, I can add one more thing. And that is, I hope my audio is good. But my point is not just whether p-values are appropriate or not, but whether what threshold is appropriate. But that we need to understand the reason why a given threshold may not be. And I'm talking about the inverse. So in using, we need to understand it's not about the probability that you model. It's about the probability. It's about how compatible your data, your observation is with your. I think that point is often get lost. Many people did not understand. So, given my presentation, we for the calculations of inverse probability. Even though it may be difficult for us to come up with a prior probability of our alternative hypothesis. But if we have a picture in mind, we can develop something about the inverse probability. So, with that, I think it's possible that we get some idea about whether the way that we use the p-value is appropriate. So it's not just whether you can continue to use p-value or not. It's also about developing something about the inverse. That may not be. But I can tell you that, once I realized how important this field, every time people at my age, we do medical work every year, right? And unusually, and nowadays, when I get a positive test result, I don't. I would just ask my doctor. So even that the test is positive, what's the probability that I actually have a disease? And I said, well, this base theory, simply inverse. I said, a good doctor may not actually give you the inverse of it. But a good doctor, in interpreting the test result, they will ask you a lot of questions about the content of your disease or your family of history. For example, they will ask you if your parents have the same disease, and do you smoke, do you drink, and do you use drugs, and so on. And they want to collect the contextual information before they interpret the text. Okay? Because that's the only way that you can get some idea about the inverse. So I think that's also what we do. We may not be able to come up with a number, an exact number of the first puzzle, the inverse of the puzzle. But if we pay more attention to our theory, our contextual background, the contextual background of our research, we might be in a better position to get some good idea about it. So that's what I learned.
Thank you. Great lecture, and I think this is really, really important for us to apply to our research. I think it's very practical too, and theoretically and methodologically too. Now, I think I will wrap up, and before I call it adjourned, I want to remind you for the upcoming webinar, and actually we will have another famous scholar coming aboard, and his name is Johnny Zhang, and now I'm sharing his screen, and you should be able to see that Johnny's work next week, and same time, and 10 a.m. in Taiwan, and 8 p.m. U.S. Central Time. Please join us. His topic will be on social network analysis in structural equation model framework. So for those who are interested in SEM or latent constructs or structural social network analysis, for example, and analyzing Twitter data or any network data, social media data. So Johnny is doing a lot of the really path-breaking new research. He has a lab to come up with new methods to analyze the social media data. And come join us to learn from Johnny and the latest methods, and also what his findings, which is funded by NSF, and he has a really, really interesting project and methods. And I hope you will find this interesting. And for those who are interested in social media data, big data analysis, you should not miss this lecture. by Johnny Zhang of Notre Dame University next Thursday. All right. I think, Peter, I will let you do concluding remarks.
Okay, thank you, Carl. Yes, because try to, and thank to Carl, and we try to invite as many, for those scholars that who can contribute to the matters. Because Johnny, he is from the Department of Psychology. So
Yes.
most of our guests are from government study or political science, but this time we're gonna have Johnny, who's from the Department of Psychology. I think we will have a quite different view of this. But in terms of the methods, I think we can have a lot of more to exchange and to learn from each other. And thank you for joining us today. And please stay tuned. And Professor Lin, and you're more than welcome to join us next time when if you're available. Okay, and thank you, friends, old and new, and United States and Taiwan. And good night and good day. Thank you.
All right. Thank you, Tse-min. Thank you, everyone. Thank you.
Thank you, Professor.
Look forward to seeing you next week. Bye.
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 Yeah,
Thank you.
pleasure ours. Yeah. Thank you. Bye.
Thank you, Dr. Ho. Good night.
Oh, sure. Sure. I hope you enjoyed this and keep.
Oh, I did.
Yeah.
That's every week.
Great question. Great questions.
Oh,
yeah,
thank you.
this
Thank
is a
you
great
for that.
dialogue. Yeah.
Thank you, Dr.
Yeah.
Ho, Dr. Pan.
There are more
it.
talks upcoming. I think you enjoy it. Yeah.
I thought
Yeah.
you make a
Stay
mistake. You accidentally told Dr. Clark that this p-value lecture is next week. You did say that.
Oh, did I say
So
next
he probably
week?
missed
Oh,
that.
that's it.
But he can read the watch
week,
the recording anyways. But thank you, Dr. Ho. I appreciate it.
Yeah. Okay.
Good night.
Okay. Next week actually will be Johnny. Yeah. All right. Okay.
Awesome.
Thank you for
Awesome.
reminding
Thank
me.
you. Look forward to
All
it.
right.
Bye-bye.
Thank you all. Bye. Thank you.
Thank you.
Bye. Okay, I think we're good. Okay.